In this video, I'll talk about sensitivity analysis methods for structural equation modeling. This is a new idea that I hope will gain momentum because sensitivity analysis would give stronger evidence of a validity of a structural equation model. So in general, the objective of sensitivity analysis is to uh, quantify the extent that results would change if different decisions were made about your model. Now, there are different types of sensitivity analysis. There is sensitivity analysis to missing data, for example. There is sensitivity analysis to outliers. And here I'm going to specifically talk about one type of sensitivity analysis that's already popular in the field of causal inference, which is sensitivity analysis to omitted confounders. So omitted confounders are variables that are not included in the model, but they are related to observed variables. Therefore, if they were included in the model, they would alter the conclusions of the study. So the objective of sensitivity analysis to omitted confounders is to quantify how strongly this confounder needs to be related to the variables of the study for the conclusions of the study to change. So the first sensitivity analysis for omitted confounders was conducted by Corderfield in 1959. It had to do with research that was going on then about the effects of cigarette smoking on cancer. You couldn't do an experimental design about cigarette smoking because it's unethical. So a lot of non-experimental research was done, and it was important to check for the sensitivity of those results. So the answer was, well, the question was, can an unmeasured factor which causes lung cancer, but is more common in smokers than non-smokers, explain the association between smoking and lung cancer? In other words, can a variable that was not included in the study change the results of the study if it was included? So this particular study, Corderfield found that an unmeasurement confounder would have to be 9 times more common in smokers than in non-smokers to explain the observed association between smoking and lung cancer. So as you can see, this type of sensitivity analysis gives a lot more confidence in the results of the study. Now, for structural equation modeling, there can be different types of model misspecification. And Kaplan created a taxonomy of internal misspecification versus external misspecification. So internal misspecification is what we know more commonly as a misspecified model, where there are no omitted confounders, but the relationships between the relationships between the variables in the model is both is specified incorrectly. That includes latent variables and observed variables. Now, and this type of evaluation of internal specification is done in common practice in structural equation modeling through assessment of fit, specification searches. So this is already a well-adopted practice. Now, external specification is to evaluate the possibility of an omitted confounder and what potential effect it would have in the results. And that has not been done much in structural equation modeling, but it is an area that has potential to grow. In the area of causal inference, there is a lot more development with respect to sensitivity analysis. There it's related to diagnosing omitted variable bias, confounding, or endogeneity. Now, in 2017, Harry, McNish, and Hancock developed an approach for sensitivity analysis to omitted confounders in structural equation modeling using the idea of phantom variables. So a phantom variable is a a latent variable that is placed in the structural equation model. It does not have indicators. It has a mean set to 0, a variance set to 1, and all the paths from the phantom variable are also fixed. And this phantom variable can be used to represent a confounder in the model. So the idea of phantom variable is older, and it has an application currently. If you are interested in formative measurement models, you would use phantom variables to represent uh, um, a latent variable that's a composite, a formative composite. Now, here we are using the phantom variable to represent an unmeasured confounder. So here we have a simple structural equation model to set as an example. So let's say we are interested in doing a sensitivity analysis for this model. This is our original model of interest. Okay, you can see here that there is a direct effect of x on m, there is a direct effect of m on y, and then there is an indirect effect of x on y through the mediation of m. And that indirect effect is beta 1, beta 2. Okay, here we have the implied covariance matrix. So the relationship between x and m is just beta 1 times the variance of x. And then the relationship between y and x is beta 2, beta 1 variance of x. And here we have the other covariances and variances in the model expressed in terms of parameters of the model. Now, let's say there was an omitted confounder. So now here we added z, which is an omitted confounder. Let's say z had a direct effect of x, m, and y. So it's a confounder of the relationship between x and m, confounder of the relationship between x and y, and confounds the relationship between m and y as well. So what would change if that omitted confounder was there? Now you can see that the relationship between x and m, it's no longer just a function of beta 1 variance of x. Now we have beta 1, and then we have the square of the effect of z on x plus the error variance here. And then we have again here the sensitivity parameter, which would be the effect of z o x and the effect of z o y. Okay, so you can see how the implied covariance matrix changes quite a bit because now there is this confounder here. Okay, so the sensitivity analysis is the idea of evaluating the changes that would result from this omitted confounder. Okay, so Harry, McNish, and Hancock proposed two variations of the sensitivity analysis for structural equation modeling using phantom variables. One, if you estimate your model using a frequentist approach, and a common estimators used in this case are maximum likelihood, robust maximum likelihood, weighted least squares with adjusted means and variances. In this case, you would add the phantom variable in the model and set the paths of the phantom variable to specific values that you would decide and you would vary those values to try to investigate the sensitivity of the results. So in this case here, the omitted confounder Z is being placed as an omitted variable in the model, and then two coefficients, 0.7, 0.5, were added as sensitivity parameters. So this approach would have to feed the model several times with different values for the sensitivity parameters. Remember, the sensitivity parameters like this 0.5 here are the values of the paths that are connected to the phantom variable. Now, they also created a variation of this method for if you estimate your model using a Bayesian approach. In this case, instead of setting fixed values of the sensitivity parameters, you would set the mean of the sensitivity parameters and the variance of the sensitivity parameters. So that in Bayesian terminology corresponds to set the prior distributions of the parameter. So here there is an advantage that you don't really need to set multiple values of this prior distribution, and which is less cumbersome than what is done if you're using a frequentist approach. Okay, so they recommend that you do a sensitivity analysis using the same method you did your original analysis. So if you did your original analysis with a frequentist approach, with maximal likelihood or robust maximal likelihood or WSMV, you should do a sensitivity analysis using that same estimator. But if your original analysis was a Bayesian analysis, then you can do the sensitivity analysis using the Bayesian approach. Now, the phantom variable approach was applied in an article by Leite, Stapleton, and Bettini. In their case, they were interested in this model here of the relationship between teacher participation in the teacher network and workload manageability, and also whether participation in the network moderated the relationships between perception of school management, perception of student participation, perception of teacher support, perception of student delinquency, and perception of family background, and workload manageability. So they added a phantom variable, and in this case, just with two sensitivity parameters. So there is a path from the phantom variable and participation in a teacher network, and a path from the phantom variable to workload manageability. And what they did is that they selected three values of gamma 1, the first sensitivity parameter, and three values of gamma 2, and then they fit 9 models total that were created by varying gamma 1 and gamma 2. Okay, and then they plotted the results. So the plot is shown here. So the three values of gamma 1 were 0.1, 0.25, and 0.5, and the three values of gamma 2 were also 0.1, 0.25, and 0.5. And they showed that for the effect of network manageability, the effect of participation of the network on workload manageability was sensitive to an omitted confounder, because here in the y-axis we have the p-value for that effect, and as the sensitivity parameters increases, the effect goes from non-significant to significant. Notice that 0.05 is the alpha level. So here, if you have both sensitivity parameters at 0.5, then that effect of teacher participation in a network on workload manageability becomes statistically significant. And otherwise, with lower levels of sensitivity parameters, it's not statistically significant. However, they found that the moderation effects of between student delinquency, student participation, teacher support, new teacher, school management, family background, and network participation, they were not sensitive to the omitted confounders. So you can see this flat line here that regardless of the sensitivity parameter, the p-value doesn't really change. So these were not sensitive to the omitted confounder. Now, there is a more complex approach available in the SEMsens packaging R, where it overcomes a main limitation of the Herring-McNish-Hancock approach. So in the filter variable approach, you have to specify different values of the sensitivity parameters. Remember again that the sensitivity parameters are the paths of the filter variable. And if you have a complex model, either you create very few sensitivity parameters, or you have to fit a very large number of models. So it may become very complicated. Just for example, in the Leite et al. Example, they only have 2 sensitivity parameters and 3 values of each of them, and they had to fit 9 models. For a complex model, there can be a very large number of models you'd have to fit, and this is very cumbersome. So what the SEMsens package does is implement a search algorithm called the anti-colony optimization algorithm to search for paths of filter variables and the associated sensitivity parameters that change the conclusions of the model. In that package, you can actually specify what type of conclusion you are evaluating. You want to, and the options are look for changing the size of parameter estimates, look for changes in p-values, or changing model fit. So this is a flow chart on how sensitivity analysis conducted with the SEMsens package. It first selects targets for sensitivity analysis. That's the part you have to do in preparation. Set up the sensitivity analysis model, so you put a model with all the filter variables you want, but you don't have to choose values for the sensitivity parameters. And then select an objective function. The objective function is either a function of p-values, parameter estimates, or model fit, or you can create your own combination, an objective function that maximizes a combination of these. And then you start the algorithm where it will randomly select sensitivity parameters, and it will search looking for the sensitivity parameters, looking for the set of sensitivity parameters that will optimize the objective function that you defined, either based on p-values, model fit, or size of parameter estimates. Okay, so to show an example how flexible this can be, the package has this example here where it's a very complex model of the relationship between working memory and writing with many mediators, very complex relationship. And there are, for this sensitivity analysis, there are these 9 different paths from the phantom variables to the variables in the model, and there could be an infinite number of sensitivity parameters here. So this would be very practical to do manually using the Herring-McNish and Hancock approach, because you would have to fit by hand many structural equation models. But with the edge colony algorithm, you can do that search automatically. So after running this example with the SEMsens package, specifically looking for changing p-values, um, I obtained these results here. These are paths in the model. So discourse to the grammar is the direct effect of grammar on discourse. Okay, and so in this case here, um, it shows this is just part of the results. Um, P is the original P of the analysis. P star is the P that was achieved through the sensitivity analysis. And all of this here show that the sensitivity analysis was able to find find a set of sensitivity parameters that would change the conclusion about significance. So, for example, in the first row here, the effect of grammar on discourse, the original analysis, the p-value was 0.25, which is not statistically significant. But then through the search, it became statistically significant, and the parameter had the original parameter was 0.1, but when you added a fetal variable and sensitivity parameters, the mean across the search was 0.18, so it increased quite a bit. Uh, and that corresponds to an increase in 80% during the search, or average increase. So that parameter varied quite a bit, that parameter estimate during the search. So it's very sensitive. It was very sensitive to the fetal variable, like to the misspecification. Um, Now, the effect of theory of mind on discourse, the original parameter was 0.26. It was statistically significant, but then during the search, it became not significant. And the mean through the search of that parameter was 0.06, which is a lot smaller than 0.26. And it varied quite a bit from 0.07 to 0.31. And the mean change was 38.46. So it's also very sensitive. Now, if you look here at the bottom, we can see a parameter that was not sensitive, the effect of grammar or inference. The original value was 0.29. The p-value indicated the original p-value that was statistically significant. It did not change to non-significant during the search. Okay, the mean across the search was 0.32, which is pretty similar to 0.29, and it only varied from 0.24 to 0.35. So it didn't vary that much. So this relationship here was not sensitive to an omitted confounder. Okay, another table we can obtain, this is a little bit more complicated to read, is for each path, okay, what sensitivity parameter was large. Here the table went over, but like, so let me just show here, for example, the SP2 is grammar of phantom. And so that is a path of the phantom variable. And you can see that they became quite large. So if you had a negative effect of the phantom variable on grammar, it would, of about 0.2 minus 0.2, it would change the results of the study. Now you can see the last one here is the one that really, one of the ones that was larger. The sensitivity for SP9 is writing on phantom, so it's the effect, the direct effect from the phantom variable writing. And for the results of the analysis to change, you would need strong effects of the phantom variable on writing, okay, for the results of the analysis to change. Now, so after sensitivity analysis, two scenarios can occur, but typically what you find is a combination of these two scenarios. The first scenario is that for some variables in the model, you found that the results are robust to an omitted confounder. So you find that only strong sensitivity parameters would change the conclusions of the study. In that case, you would just write a description what could be that potential confounder, but this is good news. It shows some robustness. And then for the second scenario is when you find that even weak or moderate confounders would change the results of the study. In this case, it's a limitation. We would discuss what would be these potential confounders and maybe do a follow-up analysis or theoretical revisions that could include these potential confounders. Now, a typical sensitivity analysis would have a mix of, for a complex model, would have a mix of scenario 1 for some relationships and scenario 2 for the relationships. So that's how would perform sensitivity analysis in SEM, and it's something that's highly recommended.